Hello class, and thank you for watching the second parts to 3.7. In the second part today, we're going to discuss how to actually get the inverse of a function and how to using inverse operations, review again all the inverse operations, and regardless of what type of equation we have, how do we find the inverse to those said equations. So for these examples, this is going to involve finding, interchanging, just like before, interchanging the x and y values. And very similarly to what we did in the last set of examples from yesterday's notes, from the previous video, we're going to do just inverse operations. The only difference is that we're not going to do it for a specific value of y or x in case, again, x, y, however you want to think about it, the inverse or the original function. And we're going to do it again for all values. So this is going to require us to not get one specific numerical answer, but an expression, an algebraic expression to represent the inverse of the function. So let's look at example 6a. So here, we're going to start by again switching the x and y value. Remember, this is another fancy way of saying y, and I'm going to write it like this. So I'm going to move this to the other side, to the right side of the 7x minus 5. And instead of using the f of x notation, I'm going to use the y notation. Now, step number one is that we switch the x and y value. So this equation is now going to become 7y minus 5 equals x. And to find the inverse of this is simply going to require us to use inverse operation. So the opposite operation here of adding or subtracting 5 is to add 5. So we start with any vertical translation, anything that's been added or subtracted first. So we're going to move the 5 to the other side, making it positive 5. That's going to give us now 7y equals to x plus 5. And this again is where we don't get a numerical value because we're substituting, not substituting in the value in for x. We're going to just get a general equation, a general expression in terms of x. So x and the 5 do not get added together. Now, going into our second step, because we have 7y is equal to this, the way we're going to solve this equation is by now dividing by 7. So this side gets divided by 7, and this side gets divided by 7. So this is going to be reduced, and y equals to x plus 5 over 7. And now that we have the y isolated, that is your inverse. Now the notation, remember, for inverse is this notation there. So I'm just going to write that I have the inverse of f using said notation, and here is my answer. Now what I want you to pay attention to before we finish this problem is notice that we're doing the opposite of the order of operation right here to get this number y. And this expression is going to do the opposite. Notice that the order of operation, if I do this, would be multiplication first. So if I was to plug in a number, again for x, and I was supposed to do, let's pick the number 1. The order operation will first multiply that 1 with 7, which would give us 7, and then that answer gets then subtracted by 5, and we end up with 2. So following PEMDAS, for any x value that I get, the first thing I would do, regardless if that number is 1, 8, 12, I would first multiply that number of x with the number 7. After doing that, then that answer would be then subtracted by the value of 5. So this again is following PEMDAS. Notice that the inverse is doing the opposite thing. So if I was to plug in a number here, let's say I plug in again the number 1 for x, according to this order of operation, because this is in the numerator, I will add that number 1 with 5, and then that answer will then be divided by 6. So I add 5, and then I divide, the answer is 6. I would divide that number by 7. Notice that that's the opposite of these operations here in the opposite order. So what the inverse is doing, it's undoing PEMDAS and giving us an equation that is going in the opposite direction and doing the opposite operation of what PEMDAS normally does to the original function. How neat is that? So this, like I mentioned before, is our inverse function. So now let's look at this next example here. So here we're going to do the same thing by first switching the x and the y. So we're going to write this as 5y plus 1 divided by 9, and that's going to equal to x. So for these type of equations, the inverse operation, since all of this is being grouped, all of this is being divided by 9, is to always get rid of the fraction by multiplying by the reciprocal of this value. Since all of this is being divided by 9, we have a fraction where the denominator is 9. The first thing to do is to multiply everything by 9. So we're going to multiply this side by 9, and we're going to multiply this side here by 9. That way this 9 and this 9 can divide themselves out, and we have 5y plus 1 equals 9 times x, which is 9x. And now we just do the same thing that we did in the previous example. We'll start by moving our constants. In this case, we're going to move the 1, which will now turn into a negative 1 to the other side. 5y is equal to 9x minus 1. That's the only thing that changes. We now have a coefficient of 9 instead of the 1x. And then, just like the last example, we would divide by 5. And there is your inverse function. Y equals to 9x minus 1, all being divided by 5. So with this just being divided by a value, we just start off with that and then do the same 2 steps as the previous example. So again, we're just scaffolding and just adding that 1 extra step. Now for a function that looks like this, the way to get the inverse of this, again, first switching the y with the x, so 5 over y is equal to x, is to simply get the reciprocal. You can do cross multiplication, which is a normal thing to do, but in this situation, since I'm looking for the value of y and y is in the denominator, I simply have to get the reciprocal. So if I write this as y over 5, I just have to do the exact same thing to the other side, to the right side of the equation. And since this is technically x divided by 1, this would be 1 over x. I can then again, like the last example, because I have a denominator, the way to get rid of the denominator is to multiply by that denominator. So I'm going to multiply both sides of our equation by 5. That way this cancels out. We have the y by itself, and now we can multiply 1 over x with 5. Well, how do we do that? To multiply a fraction with a whole number, you simply multiply the numerator with the whole number, so 1 times 5, and then you put it over the denominator x. So there is your inverse. Now I didn't do this on the last example, but I'm going to go back and write the inverse notation for this. So instead of x, I'll write f inverse, and there is your inverse function. Now, if you pay very close attention, is the exact same thing as identical as the original function. So very neat how the inverse and this reciprocal function are the same. They're the exact same function. Now, this next example looks very similar to the previous example. So let's write this again in, let's start by switching the x and the y. Remember this, f of x is the exact same thing as y. I'm just writing it on the right side of the x over 6. So replacing the x for y and the y for x, we get this there. And it looks very similar because it already alternated again the y. The y is already in the numerator. And because we have a fraction, the way, again, like the last 3 examples, the way we get rid of the fraction is to multiply by the reciprocal, by multiplying by that denominator. So the reciprocal of 1 over 6, which is just 6. So by doing that, this 6 and this 6 divide out, and we're left with y equals to 6 times x. So there is the inverse to x over 6. And this is a little bit more intuitive, because if you think about what PEMDAS is doing up here, y equals to x divided by 6, is getting a value of x and dividing it by 6. X divided by 6. And if you look at the inverse, notice that the inverse of dividing is multiplication. X multiplied by 6. So again, this one's a little bit more intuitive to understand exactly what the relationship is between the function and its inverse, how it's actually doing the opposite of the original function itself. Now I want to go back and do one very similar to the first example, with the only difference of having a negative coefficient for x. So we'll start again by switching the y for the x and the x for the y, and then solving this equation for y. So just like example A, we'll start by moving our constant to this side. So that will change the positive 8 to a negative 8. Negative 3y equals to x minus 8. And we'll divide by negative 3. So y will equal to x minus 8 over negative 3. Now the reason I wanted to go over this one is because, again, what do we do when we have a negative coefficient we're dividing by a negative number? Well, you could leave it exactly as it is, and nothing will be wrong with that. But in most cases, it looks kind of weird, at least in my opinion, it looks weird to have a negative value there. So recall that both of these numbers up here in the numerator are both being divided by negative 3, and specifically by that negative sign as well. So if I divide both of these by this negative sign, that's going to make the positive x into a negative x, and the negative 8, into a positive 8. And that changes this to a positive 3, which to me looks a lot nicer as compared to having a negative sign down here. But like I mentioned, there's nothing wrong with having the negative sign like that. It just looks cleaner, in my opinion, to have the numerator have the negative sign in it than the denominator there. And this also can be cleaned up a little bit more, because it's not normal practice in order to have a leading coefficient to be negative in these situations. And we can switch it and again get the commutative order of this. So instead of negative x plus 8, we can do 8 plus a negative x, which will look like this, divided by 3. But like I mentioned earlier, this is still going to be acceptable, and that is also going to be acceptable. But I just wanted to go over an example of how we can clean this up when we have a negative value. Okay, so just like yesterday, now let's go into examples where we have powers on our x. So again, like normally, we're going to start by switching the x for y and y for x. So we have 8y to the third plus 5, and we're going to set that equal to this x value. So we'll start the same way as the letters A and even the previous example, by moving our constant to the other side. And notice again, the steps always start the same way. So we have 8y to the third power equals to x minus 5. And our second step will be the same as in example A. We want to get rid of this coefficient, so we'll divide everything by 8. So y to the third power equals x minus 5 divided by 8. So now that we got this, our next step here is to get rid of the exponent of 3. And like I mentioned yesterday in the other video, anything to the third power or to any power is the inverse of that would be some type of root, a square root of some type. Not a square root, but some root of some type. So since we have y to the third power, the root that we're going to use here will be the root where the index matches again to the power of this, the respective power. So the third root. And what I do to one side, I obviously have to do to the other side as well. So I also have to take the third root of this side there. So we're going to end up with y equals to the third root of x minus 5 divided by 8. And there is your inverse. So let's go now to the next page, and let's just again continue again differentiating this and seeing what happens when we add more things. So from the last example, we now know how to get rid of this power of 3, okay? But we have to isolate that part. Notice that the x plus 4 is part of the group that's being raised to the third power. So we have already switching the x and the y. We're going to start by first moving the 1 to this side there. So again, same first step as before. Sorry, that should be negative. So that cancels that out, and we end up with y plus 4 is raised to the third power, and that equals to x minus 1. So now with this right here, we can now get rid of the power of 3 using the same root as before. We cannot mess with the y plus 4 and try to move the 4 to the other side, just like the way we moved the 1, because it's being grouped as part of the value that's being raised to the third power. So we first need to get rid of that power there before we can do anything with the y. So using, like I said, the cube root, just like the previous example, we end up with y plus 4 equals to the cube root of x minus 1. Now, pay very close attention again of how we're just scaffolding and building again our additional steps of how we solve this. So from the previous example, if I just had x to the third plus 1 equal to x, or y, sorry, this should be a y and this should be an x. The first step would be to move this over, so y to the third will equal to x minus 1, and then taking the cube root, and I would be done. But because of this plus 4 that we have inside there, we now have to consider and what to do with that plus 4. So again, look at this and compare it to that. Notice that the only difference is that we're adding this one extra step now at the end, having gotten rid of that value there, the power of 3 from this side of the equation, by taking the cube root to both sides. So again, it's just building on prior knowledge, prior abilities, prior steps, and just increasing again or adding an additional scaffolding, an additional step at the end. So this is now going to move the 4 to the other side, just like the way we would move the 1. The only difference is that it would not be included or added or subtracted to this value here. All of this is being grouped together. You have to recall that this symbol right here is grouping this y minus, this x minus 1. So if I was to plug in a number, I would first have to subtract the 1, get that value, and then take the cube root before I can do anything with this value there. So because of that, I have to keep it separated. So my inverse of f would be the cube root of x minus 1, and I'm going to put a little bar right here indicating that that's the end of the group, and then minus 4 at the end. So let's skip letter H for right now and let's talk about letter I, since that correlates again to the example we just did. So for this problem here, 4 times x minus 5 to the third power, we'll switch the y for the x for the y minus 1, and we're going to set it equal to x. So very similar to the last one, we have again a power of 3, but we have this additional number right there. We start the same way as before by getting rid of this constant that's on the outside of the parentheses there. So we're going to move it to this side, changing it from a -1 to a +1. So we have 4y minus 5 to the third power equals x plus 1. Now, because of this 4, before we can take the root here, like we did on the previous example, this has to be divided out. Since 4 parentheses means multiplication, the inverse operation would be to divide. So if I divide both of these values, both sides of this equation by 4, that's going to reduce this value out. So 4 divided by 4 is going to become 1, leaving us with y minus 5 to the third power equals to x plus 1 divided by 4. So it's not very different than doing the example from the previous page where we followed the exact same steps. We had 4, let me remember that example, it was 8y. 8y to the third plus 5 equals to x. And notice that the first two steps are the same. We move this over and then divide again by this 8, and we end up again with that same thing. And then we're going to take the root. So we're going to end up doing the exact same thing and now taking the roots like we did. We would end up with y to the third equals to x minus 5 divided by 8. And we ended up with the third root of this, as you saw from the previous page. Now the only difference is that because we have an additional value inside, we're going to have to again consider that step right there, what to do with that at the very end. So let me erase this, and let's get rid of that power of 3 by taking the third root. So y minus 5 equals to the third root of x plus 1 divided by 4. And just like the previous example, just like the example up here, we can now get rid of the number and the operation that was inside the parentheses. In this scenario, we're subtracting 5, so we'll move the 5 to the opposite side, making it a positive 5. And again, just like before, all of this is grouped together. We would have to perform all these inside operations first, and then take the cube root before we're even allowed to add this 5 there. So our inverse operation will look like this. It would be 3, the cube root of 3 of x plus 1 divided by 4. And I'm going to group this together. I'm going to put this down just to indicate that that's all grouped together. And then plus 5. And I'm doing this obviously in the notes. You won't be able to do this on the homework. But just again on our notes, on our scratch paper, to remind us, okay, all of that's being grouped together. And then this plus 5 is on the outside of this radical symbol here. All right, changing gears here. Now let's talk about square roots. Instead of powers, let's talk about roots and how we get rid of roots. So here, to get the inverse, like always, we're going to switch the y for the x and the x for the y. So here we'll have the square root of the letter y instead of x, plus 4, and it's going to equal to the x value instead of y. And we're going to solve this equation starting with the same thing as before by moving our constant to the other side. So this will require moving this positive 4 to the right side of the equation and make negative 4. So now we have the square root of y equals to x minus 4. Now to get rid of a root requires just the appropriate and the corresponding power. Since this is a square root, a root with index 2, all right, the power we're going to use is going to be a power of 2. So x minus 4 to the second power. So our inverse would be y equals to x minus 4 to the second power. Let me just write it as a function notation with the negative sign there and there. There is your answer. Okay, I'm going to skip letter I, go to letter J right now because it has a root, and we're adding just one extra step here. We have a plus 4 inside the roots instead of having nothing inside like the previous example. So we have the third root of y plus 4. The minus 5 is on the outside of that root, and that will equal to our x. So again, like always, the first step is to get rid of any of these vertical translations. So the minus 5 will be changed to plus 5. And we have the cube root of y plus 4 equals x plus 5. And because the root is 3, it's a cube root, the appropriate power here would be the third power. So by raising both sides to the third power, that will get rid of the root. We end up with y plus 4 equals x plus 5 to the power of 3. Now, to solve this, now that we did this, we could do the exact same thing that we did in the previous example up here, okay? Is again just to move the 4 out of the way. So you see a lot of these steps are just recycled steps, and you're doing the exact same thing. And if you're able to do one, then you should be able to do again an infinite amount of them because the procedure is going to be the same. The only thing that's going to be different is going to be possibly those numbers. But as long as you know again what the inverse is and what the procedure is, then you could do again any problem. And we'll end up with, well, negative 5 because we're going to move to the other side, making it from positive to negative. Not 5, 4, I'm sorry. Our inverse is x plus 5 to the third power minus 4. Okay, so let's now move on to example 7. Let's talk about inverse functions and how to determine if two functions are inverses. Well, two functions can be determined to be inverses if the composition of those two functions results in only the variable x. And both again, and the commutative or not commutative, but the opposite order also results in f. So to show that two functions are inverses, you have to show that both f of g of x and g of f of x both equal to the value of x. So let's see an example of this. So here I have the function f and g, and I want to determine if these two things are inverses of each other. So instead of identifying again and creating the inverse of this, doing the inverse operations to see what this equals when I switch the x and the y, all I have to do is simply do the composition and first do f of g of x, which means that we're going to get to this g function and plug it into the x of the f function. So this would be 2 times x minus 3, and for the x where I have the parentheses, I'm going to write the rule for g, which is 1/2 x plus 3 over 2. So to simplify this, let's see what this is going to simplify to. This will require first distribution. So multiplying half with 2, that's going to be 1x. So I'll just write an x. Distributing again the 2 into the 3 over 2, that would multiply and give us 3. So we can get rid of the parentheses and we'll bring down this 3 at the end. Now combining these two terms give us the value of x. So as you see right here, fog of x gives us just the value of x. All we have to do is prove that we end up with the same thing, the value of x, when I do the substitution in the opposite order. So now let's do the gulf of x. So starting off with g of x is 1/2 times our x value plus 3 over 2. And again, what I'm going to do here is replace the x value with f. So 2x minus 3. I'm putting f inside there. Just like over here, inside here, I put g. So now the steps again are going to require distribution. So now I have to multiply both of these numbers by half. Well, half times 2, that equals to 1. So 1x, which I'll just write as x. Half of negative 3 is negative 1.5 as a fraction. That's negative 3 over 2. Bring down the plus 3 over 2. And now I can combine these two terms. Since a positive and a negative are 0, we end up with 0 there. So negative 3 over 2 plus a positive 3 over 2 is 0. So we just end up with x. So you see here, these two things are inverses of each other because when we do the composition, the operations are going to cancel themselves out and leaving us only with the identity value of x, 1x. So what does this mean? This means that g is equal to the inverse of, f is equal to the inverse of g, and g equals to the inverse of f. So these things are inverses of each other. Now let's check the second example. So we're going to do the exact same thing. Start by getting the composition of fog. So we have x squared plus 10. And inside here again, we're going to write in g, which is the square root of x minus 10. There's nothing to distribute here, okay? And you see that all of this is being raised to the second power. Well, square root and square are inverses of each other, so they do cancel each other out. So we'll only be left with the x minus 10, no parentheses, no more square roots. Bring down the 10, and look again, we end up with x. So this equals to x. We now just have to verify that we end up with the same thing when we do the substitution to do the composition in the opposite order. So over here on the right, let's do golf of x. So we have the square root of x minus 10. And again, we're going to replace the x, what's in the parentheses, we're going to write in f inside there, which is x squared plus 10. So we're going to write x squared plus 10. Since everything is inside the square root, we can get rid of the parentheses. So x squared plus 10 minus 10. These two terms are opposites of each other. So positive 10 minus 10, that's going to become 0. And just like last time, the square root and square are inverses. They also cancel each other out. So g of f of x equals yet again to the value of x. And well, what does this mean? This ultimately simply means that f is the inverse of g, and that g is the inverse of f. That yes, these two things are inverses of each other. Sorry, I wrote this one backwards. That g is the inverse of f. Okay, so just one last time, let's verify that these two things are going to be inverses. So 6 divided by the x value minus 4. And again, we're going to put g inside there, which is 6 over x, and then plus 4 there. Well, how do we simplify this? Well, since all of this is in the denominator, we can get rid of the parentheses because this should be in an invisible one right there. So let's get rid of the parentheses first. So we have 6 over x plus 4, and then the minus 4 from right here. Okay. Well, the plus and positive 4 again are inverses of each other, so that's going to become 0. So we have 6 on the top, and we have 6 over x. Well, how do we divide these two things? Well, again, like always, we want to get rid of fractions. We want to get rid of the denominators in a fraction. And because we have a fraction within a fraction, right? So we have this fraction in the denominator of this bigger fraction there. Let's get rid of the denominator here, which simply requires us to multiply. So if I multiply this bottom part with x, this x here and this x are going to cancel themselves out, leaving us only with the number 6 in the denominator. Okay? But because I multiplied the denominator by x, I have to do the same thing in the numerator and also multiply this numerator up here by x. So our 6 multiplied by x is going to become 6x. And as you see, look at this. 6 divided by 6 is going to become 1. So the composition of fog of x simply reduces down to the value of x. So the first half of this, the first direction, the fog, does give us the identity. We just have to verify yet again that the opposite order, the reverse substitution, golf, g of f of x, also results in this identity value of x. So we're going to now plug in f into g. So let's write g first. So g is 6 divided by x plus 4. And inside the parentheses, again, it's going to go in the rule for f, the equation for f, which is 6 over x minus 4. Let me do it in a different color. Let me do it in blue. 6 over x minus 4. So we have this 6 in the numerator, this fraction of 6 over x minus 4 in the denominator, and then plus 4. Well, like always, the way to, like the last time, well, not like always, but like in the last example, because we have a fraction, and in the denominator, we have a fraction within this larger fraction, let's get rid of the denominator here in this, I'm sorry, let's get the denominator right here of this fraction there. So we do the same technique as the previous example and multiply both the numerator of this larger fraction and the denominator by this x minus 4. So I'm going to multiply this bottom part by x minus 4. I'm going to multiply this top part by x minus 4 as well. These two things are going to cancel themselves out. And we're going to end up with 6 over x plus 4. I'm not going to distribute that, and you'll see why. Over, and since these things are going to cancel each other out, the only thing in the denominator, again, this is this line right there. Probably should highlight so you see what I'm, because all these fractions, that's that one. And in the denominator, we're only going to be left with the value of 6. And of course, the plus 4 right there on the right. So here, the 6's are going to reduce each other out. So instead of distributing and then dividing by 6, I'm just going to divide by the 6 automatically, so that this becomes 1, and we end up with 1x plus 4. And distributing a 1 instead of the 6 inside the parentheses, you're going to end up with x plus 4. I'm sorry, that was a minus 4. Let's fix this. This should be x minus 4 in the parentheses. So x minus 4 plus that 4, again, is just x, since this is going to become 0. So you see, yet again, the composition resulted in the identity, regardless of the order of the composition of how we substituted this. We both ended up with the identity x. So again, that means that these two things are inverses of each other. So again, the purpose of this is not having to given again that we have two equations and we want to compare and determine if these things are inverses, we don't have to create the inverse and see if it matches up to the other function. Figure out what the inverse to f is and see if it creates this function here, or vice versa. Just by substituting it in, I can do simplification, again, work on my algebra skills and simplify the expression and see that the two functions cancel each other out, leaving us only with the identity of x. And again, that's also true, obviously, with these examples here. So not having to figure out what the inverse to x squared plus 10 is and see if it gave me exactly this, I can just plug this into the x, see if it gives us x, plug this into this x right there, see that it also gives us x, so I know that these two things are inverses of each other. Now this takes us to the final page of the notes for today, which is, given a graph, how do we determine if the graph is going to have a inverse, or that an inverse is going to exist? Because even though mathematically we can get the inverse of anything, because the opposite of adding, subtracting, vice versa, multiplying is dividing, and yeah, square roots, cube roots, and cubes. So all of those things have opposite operations, but that doesn't mean that the inverse itself is going to be a function. So to determine if the inverse is going to be a function, we use what's called the horizontal line test, and to determine if we have a one-to-one relationship between these two, a one-to-one relation between the x and y values, to determine if the inverse is going to be a function as well. Now we've talked about one-to-ones before in previous lesson. We're now just going to correlate it to how it relates again to the inverse. So a function has an inverse that is f to the negative 1 power if there is no horizontal line that intersects the graph of f at more than 1 point. And if it does that, we refer to those functions as invertible. An invertible function is a function in which no two x values or x components first components have the same second component. So if x1 and y1, if x1 and x2 are different, then the y values are also going to be different. And how does this relate? Well, only these invertible functions have an inverse function, which means that these one-to-one functions, where every x is only going to have one y and every y is going to have one x, these invertible functions, this is going to exist. So only invertible functions, or aka one-to-one, are going to have inverses that are going to be functions themselves. So taking into account example 8a and 8b, all right? Both of these are functions. You can identify that they're functions using the vertical line test. So if I draw a vertical line, vertical line, vertical line, each vertical line only intersects the relation at one location. So aka these are both functions. So this is a function, and this is also a function. But in order for it to be one-to-one, in order for it to be invertible, that means that if I do a horizontal line, that the horizontal line will do the same thing as the vertical line and only intersect the function at one place. So the horizontal line intersects the function at one place there. So, but this one over here doesn't. Notice that this horizontal line intersects the function at two locations. So that means that this function here is one-to-one. Another way of saying invertible, okay? And this one is not one-to-one. It is not invertible. Well, what does that mean in terms of the inverse? That doesn't mean that we can't get the opposite operations of whatever creates this thing right here. It just means that the equation that we create by getting the opposite operations of this one is not going to be a function itself. So F inverse does not exist. And again, don't get it twisted. Don't think that I cannot get the opposite operations of x to the second power plus whatever this number is, 5, let's say, okay? Yeah, I can get the opposite of that. That just means that the inverse is not going to be a function, that's all. So when I write this, I'm not saying that I can do the opposite operation of whatever the operations are that give me this graph, like x squared plus 5. It just means that the function, the inverse, is not going to be a function at all, okay? So F inverse doesn't exist means that the inverse is not a function. While over here, it is. This is one-to-one. So that means that F inverse is going to exist. So for these last two, same idea. Now, I don't have an example of this, but of course, these things would have to be functions first of all. So if one of these graphs is not a function, let's say that this one looked like this instead, that wouldn't be a function. So I have to worry about being invertible or the inverse existing because it's not a function at all, okay? The only way a function can have an inverse, or for the F inverse to exist, we have to first of all start off with a function. So this again is a function. So first of all, this again is a function. It passes the vertical line test. This one too is a function. Now the question is, which one of these are going to be invertible and which one is not? Which one is going to have the inverse be a function itself, and which one is going to see that the inverse is not a function? Well, using the horizontal line test, we see that this graph intersects this horizontal line or any other horizontal line multiple places. So this is not going to be a one-to-one. So not one-to-one, which again means that the inverse doesn't exist. And here, this is invertible. And remember, the word invertible and one-to-one mean the same thing. That's why I'm interchanging again the terms. So this inverse does exist, or the inverse is going to be a function. So one more time, this means that the inverse is a function. This means that the inverse is not a function. So that concludes the second part of 3.7 inverse functions. If you have any questions or still confused about anything, again, please send me a message through email, or just click on message your instructor on my open math homework assignments. Like always, I appreciate you watching, and I hope you have a good day. Goodbye.